this lecture we will go to new way of estimating the population parameter. That method is called maximum likelihood estimation. In our previous class we have estimated the population parameter with the help of least square, or we can say with the help of method of moments. This method of estimating population parameter has lot of advantages over that two method that we will see in this class. The agenda for this class is to provide an intuition behind maximum likelihood principle and theory and examples. So, what we are going to do, we remember in the previous class with the help of x bar we have predicted the mean, with the help of sample variance we have predicted the population variance with the help of moment. In the regression model we have used least square estimate. What you have done in this? The sum of the square of the error is minimized when we draw the best regression equation. Instead of that one we are going to use another way of estimating population parameter with the help of maximum likelihood estimation. This is very simple. With the help of this maximum likelihood estimate you can estimate parameter of any population. It may be any distribution, it may be a binomial, it may be a Poisson, it may be a exponential. What is the assumption we are having in the least square estimate is that error term should follow normal distribution. Whenever the error term not following normal distribution, the maximum likelihood estimate is the best way, that we will see in this class. What is maximum likelihood estimation? The method of maximum likelihood was first introduced by R.A. Fisher, a genetist and statistician in 1920s. Most statisticians recommend this method at least when the sample size is large, since the resulting estimator have certain desirable efficiency properties. Maximum likelihood estimation is a method to find most likely density function that would have generated the data. So, what we can do with the help of this MLE is that which distribution has generated the data, that we can find out. Otherwise this data set is suitable for what kind of distribution. But one assumption we have to have this maximum likelihood estimation is that it requires that one to make distribution assumption first. So, in advance we have to assume which distribution has generated that set of data. Let us see the intuitive view on the likelihood. See, there are some data set is there in the bottom. See, there are this data set. We want to know from which normal distribution this data set might have come. There are three possibilities. One is the green line whose mean is -2, variance is 1. There is another one is blue whose mean is 0 and the variance is 1. The last one is mean equal to 0, the variance is 4. So, the most suitable for this one is the blue one, because that covers all the data set. So, the purpose of maximum likelihood principle is, suppose there are some data, this data has come from which distribution. So, that kind of testing can be done with the help of this. Otherwise this data set is suitable for what kind of distribution, the other way also. So, this is most useful for estimating many population parameters. We will take a simple example. With the help of this example I will explain what is the application of this maximum likelihood estimation. This problem is taken from this book Probability and Statistics for Engineering and Sciences by Professor J.L. Devore, 8th edition. It is a Cengage publications. The problem says a sample of 10 new bike helmets manufactured by a certain company is obtained. Upon testing it is found that the first, third and 10th helmets are flawed, whereas the others are not. Let P is the probability of flawed helmet, that is P is the proportion of all such helmets that are flawed. Define Bernoulli random variable x1, x2 and so on up to x10 by we are going to use x1 equal to 1 if the helmet is flawed. If there is a defect, x1 equal to 0 if the helmet is not defective. Like that, if x10 value equal to 1 if the 10th helmet is flawed, 0 if the 10th helmet is not flawed, defective. Then for the obtained sample, say x1 equal to x3 equal to x10 equal to 1, because already is given, only the first and third and 10th helmet have some defect, and the other 7 xi's are all 0, the values are 0. The probability mass function of any particular xi is p power x 1 minus p to the power 1 minus x, which becomes p if xi equal to 1 and 1 minus p when xi equal to 0. Now suppose the conditions of various helmets are independent of one another, because this assumption is very important. If there is independent, we can find out their joint distribution. This implies that xi's are independent, so that their joint probability mass function is the product of their individual probability mass function. Since it is a joint probability mass function, see that we have multiplied for all possibilities pi into 1 minus pi, like by considering all possibilities. So when you simplify that, p power cube into 1 minus p power 7, this equation is 1. Suppose in that equation, this left hand side, this value is called maximum, this is the likelihood value, the whatever in the left hand side, I will define it later what is the likelihood value. The left hand side value is called likelihood value. Suppose with the p equal to 0.25, then the probability of observing the sample that we actually obtained is 0.002086. So like that we can supply different p value. Suppose instead of 0.25 you supply p equal to 0.5, then the probability is 0.0097. You see that when it is a 0.5, 0.25, 0.002, when it is a 0.5 it is becoming very low. So the in between this 0.25 and 0.50 we are going to get the value of p that will maximize our left hand side value. For what value of p is the obtained sample most likely to have occurred? That was the question. What is that? For what value of p is the obtained sample most likely to have occurred? That is, for what value of p is the joint PMF, this one, as large as it can be. Otherwise, what value of p maximizes equation 1? That p value is nothing but your likelihood value. Figure shows a graph of likelihood of that value equation 1 as a function of p. So what happened in x axis, we have taken different value of p. Previously just for one case we have taken p value 0.25 and 0.50. See, when it is a 0.25 this was the likelihood value, 0.5 this was the likelihood value. So we are going to draw a graph by supplying different value of p in equation 1, then we have to find out the likelihood value. This figure shows a graph of likelihood as a function of p. It appears that the graph reaches its peak above 0.3, when the value is 0.3 the graph reaches its peak, equal to the proportion of flawed helmets in the sample. Okay. Now what we are going to do? We are going to take the log of this function. I will explain there was a reason for that. Graph of the natural logarithm of likelihood. Figure shows graph of the natural logarithm equation 1. Since the logarithm of g of u is a strictly increasing function of gu, finding u to maximize the function g of u is the same as finding u to maximize log of g of u. So what is happening is, whether g of u and logarithm of g of u is the same, this figure shows a graph of the natural logarithm of equation 1. Since log of g of u is strictly increasing function of g of u, finding u to maximize the function of g of u is the same as finding u to maximize log of g of u. So the u is same whether it is g of u or log of g of u. We can verify our visual impression by using calculus to find out the value of p that maximizes equation 1. Working with the natural logarithm of the joint probability mass function is often easier than working with the joint PMF itself, since the joint PMF is typically a product. So, the logarithm will be a sum. That is the advantage of taking log of that. So, what will happen previously in equation 1, we got pq multiplied by 1 minus p power 7. I am going back here, this one, we are going to take log of this. When you take log of this, it will become, because there is a multiplication, so this will become log of p3 plus log of 1 minus p to the power 7. So, this will become 3 log of p plus 7 ln, this is ln, 7 log of 1 minus p. Next one is that functions we have to see it is the when it will the value become maximum. We know that in our school might have studied, you see, to find out the maximum value, maxima minima, for example, the maximum value we say dy by dx equal to 0, then d square by dx square will be less than 0, means that point will become the maximum. So, this equation, this is a function of p. So, we are going to differentiate that log function with respect to p. So, when you differentiate this one, so 3 log of p is 1 by p, so 3 by p plus 7 is the constant, log of 1 minus p is, this is differentiation of differentiation, log of x equal to 1 by x. So, 1 divided by 1 minus p, again you have to differentiate this function, differentiation of differentiation. So, 0 minus 1, so it will be minus 1. So, 3 by p minus 7 divided by 1 minus p. So, this equations we have to equate it to 0, because we know d of dp should be equal to 0, then we have to find out the p. So, that value that the function will get maximized. Equating this derivatives to 0 and solving for p, it gives 3 into 1 minus p equal to 7p. So, 3 equal to 7p, so p equal to 0.3 is conjectured. So, now what is happening? Previously we have substituted different values, now we have, using the concept of maxima, we have realized that when the p equal to 0.3, the function is get maximized. So, it is called the maximum likelihood estimate, because it is the parameter value that maximizes the likelihood of the observed sample. So, this p equal to 0.3 will be is nothing but this is an estimate for the population. In general, second derivative should be maximum to make sure the maximum has been obtained, but here this is obvious from the figure. So, actually we have to differentiate one more time and we have to see whether it is becoming negative or not, because by looking at the figure it seems that that point is maximum. So, what is happening, this value p equal to 0.3 is called the maximum likelihood estimate. So, what is happening, the binomial distribution of the population parameter p, we have estimated it is 0.3. So, the advantage of this maximum likelihood function is it is helping to estimate parameter of any distribution. Suppose that rather than being told the condition of every helmet, we had only been informed that 3 of the 10 were flawed, then we would have to observe the value of binomial random variable x equal to the number of flawed helmets. When you substitute 10x, 10cx p power x into 1 minus 10 minus x, when you substitute x equal to 3, this is 10c3 p3 into 1 minus p power 7. We need not bother about the coefficient 10c3, because that is not functional, just a constant is. So, what they say, the binomial coefficient 10c3 is irrelevant to maximization. So, again the p equal to 0.3. Next we will define what is maximum likelihood function. There are two terms there, one is likelihood function, next one is maximum likelihood function. First I will say what is likelihood function, then we will go to what is maximum likelihood function. Let x1, x2 and x1 have a joint probability mass function or probability density function, call it as f of x1, x2 up to xn colon theta 1, theta 2 and theta m, where the parameters theta 1, theta 2 and theta m have unknown values. here the parameter is theta 1, theta 2 is unknown values, where x1, x2, xn are the observed sample values, then this equation A is regarded as the function of theta 1, theta 2 m, it is called likelihood function. So, this is the likelihood function. So, this function is likelihood function. The maximum likelihood estimates theta 1 hat, theta 2 hat, theta m hat are those values of theta i's that maximizes the likelihood function, so that f of x1 comma x2 up to x1 colon theta 1 hat, theta 2 hat up to theta m is greater than or equal to f of x1, x2, x3 up to xn colon theta 1, theta 2, theta m for all values of theta 1, theta 2 and theta m. When the capital Xi's are substituted in place of small xi's, the maximum likelihood estimates result. So, what you have to do that one, in the capital Xi's we have to substitute small xi's, that will be the maximum likelihood estimate result. So, what we are doing here, we are finding joint probability mass function, then with the help of sample values we are predicting the population parameter. How will you interpret that one? The likelihood function tells us how likely the observed sample is as a function of possible parameter values. So, maximizing the likelihood gives the parameter values for which the observed sample is most likely to have been generated, that is the parameter values that agree most closely with the observed data. Otherwise, we can say in other way that this data set is more suitable for what kind of distributions or what kind of models. Now, we will go for estimation of Poisson parameter. Suppose we have data generated from a Poisson distribution, we want to estimate the parameter of Poisson distribution. The Poisson distribution having only one parameter, because in Poisson distribution it is a uniparametric distribution, it has only one parameter, that is where the mean and variance is same. The probability of observing a particular random variable p of x equal to e of minus u mu power x divided by x factorial. So, joint likelihood by multiplying the individual probabilities together. So, what we will do, the first step is you have to find out the joint probability function. So, e power minus u mu to the power x1 divided by x1 factorial multiplied by e power minus u mu to the power x2 divided by x2 factorial and so on, multiply e power minus mu to the power xn divided by xn factorial. So, this can be written as product of e power minus u mu power xi, because it is a product, there is a n time. If you expand it, so e power minus nu, because it will come up to n times, so mu to the power n x bar. Next we have to take the log of this, we will see that. Note that the likelihood function, that factorials have disappeared, we need not bother about the factorials because that is not going to affect the result. This is because they provide a constant that does not influence the relative likelihood of different values of the parameter. Whether we use the constant or not, that is not required, because that will not affect our the end result. It is usual to work with the log likelihood rather than likelihood, because we have seen previously when you take log of likelihood, the differentiation is easy. Note that maximizing the log likelihood is equivalent to the maximizing likelihood, this also we have seen in the previous slide. So, this was the likelihood function, you take log of that one. So, e power, when you take log of e to the power minus nu is minus nu, because it is the product, in log it will become sum n x bar log of u. Now, you differentiate with respect to u, when you differentiate it and equate it to 0, then you are getting x bar equal to mu. So, what is the result is, the sample mean is the best estimate to predict the population mean of a Poisson distribution. Now, we will go for another distribution, that is estimation of exponential distribution parameter. Suppose x1, x2, xn is a random sample from an exponential distribution with the parameter lambda. Because of independence, the likelihood function is the product of individual PDFs. Here also lambda e power to the lambda e power minus lambda x1 will extend lambda e power minus lambda x2 up to, you have to multiply lambda e to the power minus lambda x1. So, when you simplify that, it will become lambda to the power n e to the power minus lambda sigma of xi. When you take log of this, it will become n log lambda minus lambda e power x, then this has to be equated to 0. So, when you equate it to 0, so lambda become lambda equal to n divided by sigma xi, that is nothing but the inverse of the sample mean. So, this was the result. So, what happening is, now the inverse of sample mean is nothing but the mean of our exponential distribution. Now, we will go for estimation of parameter of a normal distribution. This was very interesting because we can say normal distribution is we can say father of all the distributions. Many times if you are not knowing the nature of the distribution, you can assume that it follow normal distribution. As usual, the likelihood function for a normal distribution is, we know that the PDF probability density function is 1 by root of 2 pi sigma square e to the power minus x1 minus mu whole square divided by 2 sigma square. So, like that there is a term 1, term 2, up to nth term we can go for that. So, term 1, that is when is x1, when you substitute x2, x3, so you will get different n terms. So, that is a probability mass function, joint probability function. So, when you simplify that, it is 1 divided by 2 pi sigma square to the power n minus 2 to the e power minus sigma of xi minus mu whole square divided by 2 sigma square. What will happen when you take log of this is n by 2 log of 1 minus log of 2 pi sigma square. So, what will happen, log of 1 minus, because log 1 is 0, so it will become 0 minus log of 2 pi whole square, because it will come in the, because it is x power n. So, minus n by 2 n log 2 pi sigma square minus e to the power, this one is will come in that value itself, because 2 sigma square sigma of xi minus x mu whole square. Now, what has to be done, this is the log value of likelihood function. This function, this equation has to be partially derivated with help of with respect to mu and sigma square and equated to 0, then you will get the parameter. To find the maximizing value of mu and sigma square, we must take the partial derivatives of the previous function with respect to mu and sigma square and equate them to 0 and solve the resulting two equations. Omitting the, there are a lot of details, omitting the details, we will get this result. What is this result says? With the help of sample mean, we can predict the population mean. With the help of this one, look at this one, this term is the sample variance, we can predict the population variance. So, this was the outcome of, remember this was the result of our central limit theorem also. We can prove that central limit theorem by using this maximum likelihood estimate. But one point you should be very careful, the maximum likelihood estimate of sigma square is not the unbiased estimator. Actually, we should look for unbiased estimator, but here it is not unbiased estimator. So, two different principles of estimation, unbiased and maximum likelihood, yield two different estimators. In this class, I have started the intuitive meaning of maximum likelihood principle. Then I have explained how to find out the population parameter of different distributions. First, I have seen the how to predict the population parameter of binomial distribution. Next, we have seen how to predict the parameter of Poisson distribution. Then next, we have predicted the population parameter of exponential distribution. At last, we have predicted population parameter of normal distributions. In the next class, we will take one example for predicting the parameter of normal distribution. Thank you very much.